Perfect. So what I'm going to talk about today is how you can actually increase the profitability of your plunger wells using geomagnetic sensing. So uh, historically, a lot of plunger sensors are based around the technology of electromagnetic coil. So a lot of these sensors are pretty cheap. They can be a couple $100. Basically, what happens is a piece of moving metal goes by the coil, and that coil picks up that magnetic field and creates a current. That current closes a switch. So it's very much mechanical in nature. You require a different coil for each voltage, but the principle of operation is pretty simple. There's an example of one of these types of sensors. They're strapped to the side of a lubricator or casing. But there comes a lot of issues with this technology. So slow moving or stalled plungers, if they don't go by fast enough, that change in the magnetic field isn't picked up and you don't get an arrival signal. As well, it can act as an antenna for radios and other systems. It'll trip the sensor. Things like lightning can go through a field and take down a whole bunch of controls because it has a rapid succession closure of that switch, can confuse those control systems. And then a lot of times when we're interfacing with SCADA, when it's polling that sensor signal, sometimes you get a really noisy closure or a very short duration closure that leads to missed arrivals or false arrivals. And then they're easy to burn out. So if you have stray voltages or over time, you can burn out those coils. So the interesting thing is people see the sensor as a very cheap piece or inexpensive piece of the system. It can be a couple $100, as we talked about. But when you're replacing them every 12 to 18 months, it's taking you time to go out there and replace these sensors, but you also get lost production. So if the sensor fails and your well shuts in, or your well makes an adjustment that you're not expecting, right? So it could be changing some of the times, right? It's changing the shut-in time, or it's improperly adjusting your optimization. This is leading to poor production. And so it's more than just the cost of the sensor replacement itself. And then, of course, it's one of those things that everybody has to kind of worry about. When there's a problem with a well, you're not diagnosing necessarily the problem with the well. You're first having to go, well, is it the sensor that's the problem? And it is taking away people's focus. So we realized this was happening. It's been a few years now, but we really looked at the fundamental way in which a plunger arrival is detected, and we employed a new technology. So geomagnetic sensing technology, it actually reads the Earth's magnetic field. So we're not generating a field. We don't rely on how fast the plunger is moving. What we actually do is we use a device called a magnetometer. And so a magnetometer is an integrated circuit, and it looks at the bulk amount of magnetic field it's seeing close to it. And then what we do is we tie that magnetometer into a microprocessor along with a sensitivity dial. And so the microprocessor is reading a digital signal now that is equal to the Earth's magnetic field intensity. We use a sensitivity dial just to set the level at which we're going to trip because of a plunger. So this has a lot of benefits, and we'll get into that in a minute. But those are kind of the main system components. And then the microprocessor is the one that controls the switch. And so the changing magnetic field doesn't cause the switch to open and close rapidly. We can smoothly control that switch and decide how long we're going to close it for, when we're going to open it, all of those things. So this is how it actually works. The algorithm's inside the sensor. It's taking samples of the Earth's magnetic field, and it's filtering out the noise. You get a lot of background noise. So the Earth's magnetic field can drift due to temperature. You can get background noise from other equipment. And so we filter out all these peaks and valleys, and we create a relatively stable signal. And this signal can change over time, obviously, because it could drift. And then we establish this is the baseline, or what no plunger looks like. So when it starts up, we're expecting that there's no plunger there. We come up with what the zero is. And then if we zoom out, this is actually what the baseline looks like, is this red line here. And then when the plunger comes in, it pushes and pulls the magnetic field. And this is, once again, it's not speed dependent. It's based on the amount of ferrous content in the plunger. So you can see this particular plunger has quite a bit of ferrous content. It kind of pulls and pushes the magnetic field and creates these peaks. And then what we do is as those peaks go over our threshold, which is set by the switch, we simply close the output switch. So it's quite simple in implementation once the basic technology is in place. So this is a circuit board. This is a panel of our sensor. It is a printed circuit board with surface mount components. You can see there's no moving parts, there's no coils. And so we get a lot of accuracy in the manufacturing process. And so we don't have a lot of failures when things go to the field. And then long term, it's very reliable. As well, one of the benefits here is because we put a voltage regulator on board, with coil-based sensors, you need a different coil for every voltage. In this case, we can actually take 5 volts to 24 volts, and we can regulate that down to the voltage required by the sensor. So you only have one sensor for any voltage. And then, of course, we get this immunity to noise, not only because we're reading the Earth's magnetic field, but we can take those signals and filter it out. So lightning is very, very high frequency. And so what we do is we can take that and smooth it out using software in the sensor. So it really is a computer eye, essentially. It also becomes speed or location independent. So as I mentioned, is the amount of ferrous material in the plunger is what pushes and pulls the Earth's magnetic field. So whether it's slow or not even moving at all, or even if the plunger doesn't make it to the lubricator, we can still see the change that it started to create before it got there. And so you don't have to worry so much about placement of an arrival sensor with this technology. So this is, we packaged this in a product called Cyclops. You can see here is we have the adjustable sensitivity switch. We have a pluggable connector that the wires come into, and it straps the lubricator with these mounting legs. So the adjustable sensitivity is a really good tool because it allows you to reduce the amount of false trips due to noise. So other coil-based sensors, like I said, they can trip due to lightning or other radio systems. What we can do is we can actually lower the sensitivity to be more immune to those that background noise. As well, if you're dealing with like non-ferrous plungers, like a titanium plunger or an aluminum plunger, or plungers that just don't have a lot of ferrous material, you can actually put the sensor up on the lubricator at the anvil, and you can increase the sensitivity so you can see it there. You can put it lower and turn on the sensitivity to see it before it arrives. You can see through casing or machined solid lubricators. So there's lots of ways that you can adjust the sensitivity for the circumstance in which you're deploying the sensor. And then because it is a digital sensor, we've actually made it so that this signal connection, the SIG connection, can be connected to a PC. So instead of simply just signaling to a controller, which it does in its default state, we can put it into a special mode where we can actually watch the signal and arrivals in real time. And that's what you see in the background here. Is this is actually a tool that we developed that allows you to see the magnetic field. And so when it comes to troubleshooting, you can see what's happening and make adjustments to the sensor. And then as well, we can upgrade the software. The software is replaceable. So over time, we've actually enhanced our software to refresh the sensitivity on the sensor. They were losing sensitivity over time. We built an upgrade that would make the sensor act like new again. We built another one that deals with a magnetic lubricator problem where the sensitivity is automatically adjusted for that case. So we've managed to adapt the software over time and then make that available to every sensor we've sold. So a sensor never becomes a throwaway commodity anymore. So it's a little bit different than what people are used to. So we also took the opportunity to make the product offering a lot more rugged and reliable compared to other products. So it's not just the electronics technology. We built sensors that have the best hazardous locations approval. So whether that's a zone 0 or div 1 for the intrinsically safe version, or whether that's a zone 1 explosion proof variant, there's a couple different variants there. We had a very wide temperature range. So we use industrial components. So that's minus 40 Celsius or Fahrenheit to plus 70 Celsius or plus 160 Fahrenheit because we've used these high grade components. And then we've put them in very rugged enclosures. So the IS has mounting legs, there's captive screws in the lids so they don't fall out. We've put in a 1/2-inch NPT cable port so you can use a variety of connectors. So we've just tried to make a great product that encompasses this technology. And then for tools, what we've done is either of our sensors, so this is the Cyclops and this is the Sasquatch. We'll talk about the Sasquatch in a minute, but we've actually got a device that allows you to connect our sensors to a PC. And it is using just RS-485, and you can use an RS-485 adapter off the shelf. The one special thing is the Cyclops only has a single connection. So we've included some other circuitry to make that possible because 485 requires 2 wires typically. And then we provide a free piece of software called Vision, which allows you to see these signals on your PC. Maybe I'll take a quick break and just show you how that works. Can everybody see Vision? I'm assuming you can see Vision. If you can't, let me know. This is kind of the default screen, the home screen. If you go to the setup tab here, so once again, this is available for free off our website. Just go to etcorp.ca and you can see this on your own PC. So we select Cyclops here. We tell it to connect. So I have the link device here connected to my USB port. And then on the other side, we provided a cable that plugs into the Cyclops. We just go connect. And you can see the sensor mode here. The sensor mode here it's in normal out of the factory. And when you're using it on your well, you want it to be on normal. What I've done is I've set the mode here to full debug. And there's instructions as you go through this. I can provide you some instructions later. And I'll have another course that details using these tools more if you decide to go this route. But essentially, there's on the sensitivity dial, mode 0 on the sensitivity dial allows you to communicate with it. So you can change these settings. So once the mode is set to full debug, if I go to capture, now what I can actually do is I can start capturing data. And once again, I put it back into an operational mode and it starts streaming data. So this is very much like the slides I showed you earlier. The blue is the raw samples that are coming in from the magnetometer, and the green is the baseline. So is right now you can see it's chasing it. If I adjust the position of the sensor, you can see that the green chases it. So it's auto-calibrating and that it always catches up to whatever the sensor's position is. If you leave a wrench on site, if you change a valve, it's always going to zero itself. So we'll let that zero. The red dots that you're seeing on the screen here, this is the threshold. So if I were to go and take a screwdriver and I change that threshold and I make it more sensitive, you can see that the red dots get tighter. And if I make it less sensitive, the dots spread back apart. And, you know, my screwdriver, I'm using a metal screwdriver, so it's affecting that magnetic field. But once it's sitting at steady state here, you can see that it's idling. The field isn't changing that much. And the switch up here is open. So we can actually see where the sensitivity dial's at. We can see that the switch is open. And then if I take something like a plunger, I'm going to use my cell phone here. But if the plunger were to come by, you can see it just goes outside of the range there. It's enough to close the switch and it holds it for 5 seconds and then it releases it again. And so we do have other variants of the software that allow this to hold for a longer amount of time for use with wireless systems and things like that. But we've made it so that by default for 5 seconds it's held. And the interesting thing is if the plunger keeps moving, and this is, if the plunger keeps moving up and down the lubricator, you can see that the switch holds closed the whole time. And so it's not until the plunger stops moving that it opens up that switch. So you only get one arrival indication when the plunger comes in and it bounces around. And so this is way easier to implement with SCADA. It leads to the most robust arrival sensor on the market. So I think that showing this demo shows that it becomes pretty intuitive, even though there's more underneath the hood. But I'm just going to pause this for a moment and we're going to go back to our presentation. So once again, this tool is free to download. Feel free to go there and get it yourself. There's also a really helpful resource library built into it. Another tab there has all of the certification documentation, manuals, some application notes, lots of resources there if you're interested in learning more about the sensor or deploying them on your wells. So one of the other things that, one of the reasons why we reinvented plunger sensing technology is this issue with fast plungers. So if you're not familiar with what's done on most control systems, what happens is the depth of the well combined with the arrival time at surface is typically used to calculate a velocity. It's really the only thing we have to go by. So we assume the plunger is at bottom, and then we just do a simple calculation. But this doesn't account for any acceleration or deceleration. It's just an average arrival time or average velocity. And in some cases, this is even being used for optimization and safety, but it's not an accurate number. So how do we get fast plungers? Well, if you've got inconsistent fluid loads, or the plunger didn't make it to bottom, maybe there's a hole in the tubing, our line pressure dips low, or we float a tank by lowering the line pressure. Maybe we've changed the choke at surface. So there's lots of dynamic things that can cause fast plungers at surface. And it's really the velocity at surface that we're concerned about from a safety and maintenance perspective. So what's being done right now for safety and maintenance? A lot of times we're looking at the number of trips. Oh, every 10,000 arrivals, I go and inspect my well. Or maybe I go check my springs every 6 months, because these are really the only metrics that we have available today. But not all arrivals are equal. If you've changed the mass of the plunger, well, those 10,000 arrivals could be doing more wear if you're using a 10-pound plunger as opposed to a 5-pound plunger. Well, what if it is accelerating? What if it's decelerating? If you're getting some of those 10,000 arrivals that are coming in 4 or 5 times as hard as you expect them to, maybe you're causing undue wear on your spring and it's going to fail sooner. Or if those arrivals are really light, maybe you do truly get an infinite life spring. So it really comes down to kinetic energy. So kinetic energy is just a simple calculation that uses the mass and the velocity of the plunger to give amount of force that's being absorbed by the spring. So it's really just 1/2 times the mass times by the velocity squared. And so you can see the velocity squared, the faster the velocity, the bigger the impact, right? Because it's squared, it's multiplied by itself. Repetitive fast plungers will break springs and damage lubricators over time. And it's typically not one arrival, it's fast arrivals or hard impacts again and again and again that are leading to these failures. So if you're not familiar, there's a new standard that was released last year. It's an API standard that was developed by a number of majors led by Conoco and in conjunction with a lot of the equipment manufacturers, the plunger lift lubricators and plunger manufacturers, because there was no standard governing lubricators or wellhead equipment for plunger lift, which is odd because this is one of the only pieces of wellhead equipment that gets an impact consistently. So there was definitely a gap here. And so what it really means is there's a standard now for the design and manufacturing and testing of this wellhead equipment so that wellhead operators, production operators know what the quality level of the equipment is and when it's likely to fail. And so there are several different levels that are identified. It's not just a one size fits all. So if people want a higher grade of equipment or a lower grade of equipment, they can buy that, but at least they know the standards to which it was manufactured, designed, and tested. And it's no accident that the most common or the key factor that's stamped on the side of these lubricators is a kinetic energy rating. So now we actually have a measurable number that we know whether our plunger arrivals are within spec. And so you have to actually measure kinetic energy or the velocity to be able to get kinetic energy to know if your lubricator is being operated in a safe parameter. So we built this into a sensor, a surface velocity sensor called the Sasquatch. And what it is just like you would imagine is it's 2 sensors in one. And we decided to put this on a single board. I've got it here. This is the Sasquatch. So on this single board is 2 sensors, because if you had 2 independent sensors, you can have error in the distance. You've got different clocks, different sensitivities. So to eliminate as much error as possible, we use a single microprocessor with 2 different sensors. And it's the same operating principle. You can see it in the background here is we actually have 2 waveforms and they're offset by time. So what we do is we actually look at some inflection points in this, the peaks and valleys, crossing the thresholds, and we correlate these two waveforms in time to get an average time between plunger arrivals, and then we use that to calculate the velocity at surface. And so we've put in some other advanced features, and I don't want to get into that here. We'll probably have a separate course on some of the advanced features of the Sasquatch, but if you're going and testing with the Sasquatch, we actually will calculate the kinetic energy for you. We can give you alarms on hard and dangerous arrivals. We can sum cumulative kinetic energy. So instead of going 10,000 arrivals for your maintenance, you go, let's go and look at it when it reaches some threshold of amount of impact force the spring has absorbed. So these are all really meant as like proof of concepts to give you more tools to experiment. A lot of this would probably be put in your SCADA system instead. You wouldn't expect the sensor to do it, but it's there if you want to play with it or you want to use it. So I'd like to show you a few cases. So when we first did some trials with this product, this is a major producer in the San Juan Basin in the US, where, in this particular case, they're doing some venting. So it's a 7.5 pound plunger. You can see, actually, it's kind of hard to see, but this arrival looks slower. The green is the average arrival speed. So you can see it's low. Well, but it is low because in this case, they were waiting for the plunger for a prolonged amount of time because it wasn't coming to surface. And so because the time was longer, the velocity calculation comes out longer. So this was 400 feet per minute. But you can see with the Sasquatch, we actually recorded it was over 2,000 feet a minute. And so you can see when you translate that into energy, which is in joules, instead of 7 joules of energy, what we're expecting, we got 180. So this is 25 times harder than we were anticipating. And this was happening every couple of hours. Now, somebody standing at site would hear these hard arrivals, and it's kind of intuitive that if I'm releasing the back pressure by venting it to tank to get the plunger to come to surface, of course it's going to accelerate. But a remote operator wouldn't know that that's happening, right? Unless they're looking for, oh, this cycle took longer and interpreting it. Here we're giving you the actual information that it was 25 times more energy. So here's another example. So this one's a little bit different case. Is a little bit heavier plunger, a 9 pound plunger. Once again, you can see the average velocity looks pretty consistent, around 30 joules of energy. But you can see that almost consistently, as the gas is decompressing and the fluid's unloading, it's accelerating. So instead of getting that 750 feet per minute, we're really getting about 1,200 feet per minute. Now, the thing, and this is probably what you're going to see on most wells, depending on if there's any kind of chokes or constrictions. But as the fluid can make its way down the sales line, of course, it's going to accelerate. But the interesting thing to me is more these spikes downward. So on occasion, we're getting some really slow plungers. So to me, this is telling me that the fluid load is a little bit more inconsistent. So every once in a while, we're bringing up a lot more fluid. So maybe the shut-in times are varying or the fluid production is a little different, but this is something that warrants maybe looking into it to find out what's really happening here, because maybe there's a way to run it more consistently and actually increase production. But over time, this one, long term, this spring is taking a bit more abuse than we know because it's consistently faster or harder. And then this one's a little bit more difficult to look at. This one's a well in Canada here. They were breaking a lot of their plungers and springs, and they asked us to go and monitor it to see what was happening. So it's a 10 pound plunger. The red line in this case is the average velocity. Maybe hard to read that there, but you can see once again, it looks pretty consistent. But the surface velocity, so this is in metric, but in terms of, instead of 820 feet per minute, we were getting 5623 feet per minute. So this is insane. Most plungers you don't want to run over, 1,000 or 1,500 feet per minute at most, but no wonder they were breaking stuff at over 5,000 feet per minute. And what was, once we looked at this, it was collapsing the spring like on a single arrival. And so because they weren't detecting it, they weren't shutting it in. And so they've damaged their lubricator and they have to go and replace the lubricator now. But the black dot actually shows you it's getting faster and faster. And the root cause of this one happened to be that they weren't waiting for the plunger long enough. And because they're in Canada, they couldn't vent it to bring it to surface. So what they were doing was they were shutting it in longer. And that's what the yellow is here. This is open and close. So what they would do is they were open, the plunger, the arrival wasn't being detected by the arrival sensor they were using because it was not coming quite to surface. They'd shut it in longer, build up pressure, and then it would arrive the next time, and it was a little bit fast. And then on another arrival, they didn't detect it, and then they'd shut it in for longer, and then it would just keep building and building and building until you had these kind of terminal events where it damaged the equipment.